Hi, dear audience. My name is Yang Shi, and I am an associate professor with School of Software Engineering at Tongji University. It's my great pleasure to present a brief introduction on our recent paper published in IEEE Transactions on Computers, which is titled A Lightweight White Box Encryption Scheme for Securing Distributed Embedded Devices. In the domain of computer and communication security, there are three main threat models that can distinguish the capabilities of an adversary to attack a crypto system: black box, gray box, and white box. Black box is a traditional attack model in which an adversary can access only the functionality of a crypto system. This increases the difficulty of crypto analysis, as crucial elements such as cryptographic keys or random local variables are kept secret. As you can see in the left figure, the endpoints are secure and the communication channel is insecure. Gray box models include a leakage function. In this model, the adversary can deploy side-channel attacks. As we can see in the right figure, there is a large variety of leaked information that could be captured by an adversary, such as EM emissions, power consumption, faulty outputs, timing, sound, heat, and even design details. In the white box model, which is the worst case, the adversary has total visibility of the crypto system's implementation and full control over its execution platform. Attackers can use a number of powerful general attacking techniques, such as debugging, tracing, and reverse engineering. Moreover, some special techniques have been developed. For example, the lower left figure shows the entropy attack identified by Adi Shamir, where a cryptographic key could be found in storage by searching the most chaos segment. Distributed embedded devices are widely used in the Internet of Things for gathering and sending data. Many of them are deployed in an unattended manner, such as sensor nodes, while others may be easily lost, such as smartwatches. This distributed embedded device could be potentially captured and accessed in an unauthorized manner due to their physical natures. We first investigate two typical attack patterns related to the device capture. The left figure shows the first pattern, where an adversary temporarily and stealthily captures a device without being detected and successfully extracts the embedded key without destroying the device. Then, the device is still used normally by the owner. Subsequently, the encrypted data can be easily recovered after the capture. The right figure shows the second pattern, where an adversary permanently captures a device, or a temporary capture is detected by the owner. In this scenario, the captured device cannot be used further. However, an adversary can still threaten the confidentiality of data communication by following these steps. First, eavesdrop on the encrypted communication flow and store the ciphertext. Second, capture the device and extract the cryptographic key. Third, decrypt the stored ciphertext with the acquired key. To provide practical protection for distributed embedded devices, white box encryption algorithms should be used. Because most of existing white box encryption algorithms are not sufficiently secure, we propose a novel symmetric white box encryption scheme. After analyzing the major vulnerabilities in existing white box implementations, we obtain the following 4 observations. And the design strategies of our scheme are based on these observations. Observation A. For white box implementations of standardized block ciphers, hiding the white box design in the traditional way is insufficient. Observation B. For a traditional physical network in a white box attack context, an adversary can easily recover plain texts because in the decryption process, only the input and output of the same F functions are used. Observation C. Secret physical network with a small number of rounds are insufficiently secure against some known attacks. Observation D. When constructing a secret structure based on substitution-affine networks, S-boxes in different layers share the same width, such as 8-bit to 8-bit, and thus they are vulnerable in white box attack contexts, even if those S-boxes are also secret. Motivated by the above observations, we propose the following design strategies for our new scheme. Strategy 1. According to observation A, secret structures should be used instead of standardized structures with secret keys to defeat against differential computational analysis and differential fault analysis, aiming at the standardized structures. Our proposed scheme leverages the secret structures based on the physical network. Strategy 2. For defeating attacks that are identified in observations B and C, we insert an extra pair of hijactions in the physical network. As we see in this figure, it illustrates the differences between the proposed scheme and the classical physical network. Okay, and the third design strategy is that components of different widths, such as 4-bit, 5-bit, and 6-bit, will be integrated together, and a large least common multiplier will make it hard to perform structural cryptanalysis against secret substitution-affine networks. Strategy 4. A carefully selected permutation can change a large portion of the output bits when a single input bit is changed. However, this cannot be guaranteed with a randomly generated diffusion matrix. Therefore, as compensation, our scheme adopts a transformation that maps 3 bytes of input to 1 byte of output before the linear transformation to enhance the diffusion. As we can see, this formula defines the transformation that maps 3 bytes of input to 1 byte of output. Strategy 5. Unlike most of standardized ciphers, using one layer of carefully designed S-boxes, 2 or more layers of S-boxes with different sizes will be used in the proposed scheme. Strategy 6. Although some secret components could be used in every round for specific purpose, round-dependent transformations must be involved to enhance the black box security. Technically, the core components of our white box encryption algorithm are the T-boxes. A T-box is a lookup table which transforms a 5-bit and a 6-bit inputs into a 60-bit output. The inner structure of the IST box is illustrated in this figure. The design of T-boxes follows the strategies 2, 3, and 4. T-boxes are connected with masked adders. A masked adder consists of a pair of 4-bit to 4-bit input decodings, that is, the inverse of capital H prime with a subscript, and an output encoding, that is, capital H with a subscript. The flow of the network of adders is as this. As you can see in this figure, the input values are firstly decoded and then added up. And finally, the sum is decoded. This is the flow in the network of adders. With these given components, the encryption process works as shown in this figure. For technique details, please refer to the paper. Now, we present the results of cost analysis. The left figure presents the size of ENC date and DEC date with respect to the number of rounds ranging from 10 to 32. We can see that when n equals 32, the static date only costs 259 KB for encryption, and therefore is suitable for embedded devices with limited storage. The right figure presents the number of operations with respect to the number of rounds, ranging from 10 to 32, where the mult denotes the multiplication of a matrix with a vector. The left figure shows the performance of encryption and decryption. As we can see, the proposed scheme performs well in representative embedded devices such as Raspberry Pi, Intel Galileo, and Moto 360 smartwatch. The performance of the proposed encryption algorithm has been compared with that of existing white box encryption algorithms. All experimental programs were implemented in the C programming language and executed on the 3 testing devices. The measured time cost for encrypting 1 KB date are illustrated in this figure. The figure shows that, compared with existing white box encryption algorithms, our algorithm performs much better on all the 3 embedded devices, indicating that the new scheme is more suitable for real-time applications. This is a brief introduction on our lightweight white box encryption scheme for securing distributed embedded devices. Please kindly refer to the paper for technical details. Thank you very much for your watching. We wish to express our sincerest gratitude to the editors and reviewers for their valuable comments and insightful suggestions. And we are grateful for the editor-in-chief and the entire editorial board of Transactions on Computers for giving us the great opportunity to introduce our research.